Okay, this is exam 3 for Physics 202 in spring 2010. Number 1, it says a person uses a convex lens. Remember, that's a lens that looks like this. It has a focal length of 12.5 centimeters to inspect a gem. So the gem is over here. That's your object. The lens forms an upright image. Is the image real or virtual? Alright, when it forms an upright image, that means that the magnification is greater than 0. But since magnification is equal to negative Q over P, then that means that Q, in order for the magnification to be positive, that Q has to be negative. And that means that it's a virtual image, so that's B. You focus on an object very far away, the object moves closer to you, the focal length of your eye lens has done what? So initially you're focusing on something very far away, so the light rays are parallel, so the focal point is at the back of your retina. However, when you focus on something closer, here's your retina right here, your focal point moves at this like this, so that the image is still at the retina, but it's behind the focal length. That means that the focal length has decreased. That's A. What happens to the image size in a flat mirror when you move away from the mirror? It stays the same size. If you want to set fire to a pile of leaves with a lens, you want to use a lens like this that will focus the rays, and that is a convex lens. That's A. The following figure shows the position of a mirror, the object, and the image. What type of mirror would produce the image as shown? Alright, the only mirror that will produce an inverted image is a actually, there's an error on this. Replace this mirror with a lens, and replace mirror in each of the times it says mirror, just say lens. So what kind of lens will produce an image like this? The type of lens that will produce this is a convex lens. So that is where you have a lens like this, and it produces a real but inverted image. So a convex lens. Lenses experience which of these aberrations? Okay, lenses experience spherical aberration, and because they refract the light, they also experience chromatic aberration. So the answer is C. Diffraction grating is 3,000 lines per centimeter. What is the slit spacing, D, for this grating? Well, you do 1 over 3,000. This is lines per centimeter. And that'll give you the number of lines, or the number of centimeters per line. And 1 over 3,000 is equal to 3.3 times 10 to the minus 4. That's in centimeters. And then you divide this by 100, 1 meter over 100 centimeters. That gives you 3.3 times 10 to the minus 6. That is D. Number 7 is D. The following figure shows a Michaelson Interferometer. If the source of light is a laser of wavelength lambda, what is the smallest distance to move in order to see a shift of one fringe? That is, where there was a dark fringe, you'll now have a bright fringe. Or in order to get that shift, you need a path length difference of a half of a wavelength. So in order to get that path length difference of a half of a wavelength, then this translating mirror has to move by a quarter wavelength, because the light goes here and then back again. And so you double it. The answer is B, a quarter wavelength. The following figure shows the interference pattern produced by a diffraction grating. What is the path length difference of the two waves? Alright, well, this is a path length difference of 0 lambda. This is 1/2 lambda. That's B. Alright, in a single slit diffraction pattern, what would you do to make the central bright spot narrower? So you have A sine theta equals M lambda. This gives the positions of the dark spots. If you want to make theta smaller, then what can you do? If you move the screen away, that just makes theta bigger. It makes them spread out more. If you increase the wavelength, that increases lambda, or theta rather. If you decrease the slit width, if you make it smaller, that makes theta go up, so that's not it. If you increase the slit width, that makes theta goes down, so the answer is D. These two waves, if I drop this down, I see they're offset by approximately this much, and that is a quarter wavelength, and a quarter wavelength translates into 90 degrees out of phase. What caused the diffraction pattern in this picture? Light incident on a circular object. That is A. It's a circular diffraction pattern. Place these stages in the proper order for star formation. The first stage is a cloud. That's a big cloud. They fragment into a star-forming core, and then it turns into a protostar plus disk, and then finally into a star. So that is 3, 4, 2, 1. That is option C. Number 13 is C. Number 14, why is star formation activity more readily apparent in infrared observations than in visible images? Alright, this is true. Infrared light can pass through dust. Visible light is obscured by dust. Star forming regions emit radiation in the infrared, so the answer is D, all of these. This plot has reddening and distance for a group of stars. Which of these statements best describes the location of the stars in the box on the plot? Alright, well, these stars have greater reddening. That means that their light is being reddened by the dust in a star-forming region. So they're not beside a star-forming region or in another galaxy. They're behind a star-forming core. Alright, two lenses are configured as in this figure. Their focal lengths are as shown. If the object is a distance p equal 20 centimeters to the left of lens 1, what is the final position and magnification? Alright, so P1 is equal to 20 centimeters. F1 is equal to 10. So I want to know what Q1 is. That's 1 over F minus 1 over P. The inverse of that, which is going to be 20 centimeters. And then I can find M1, which is minus Q over P. Q1 over P1. That is minus 20 over 20 is equal to negative 1. Now, my Q1 is at 20 centimeters. That means that my P2 is going to be 50 minus 20. So P2 is equal to 30 centimeters. F2 is 20 centimeters. So find Q2 is equal to 1 over F2 minus 1 over P2 to the minus 1, and that is equal to 60 centimeters. So M2 is minus Q2 over P2 minus 60 over 30 is negative 2. So in total is negative 1 times negative 2, which is equal to positive 2. So that's our magnification plus 2, and the image position is 60 centimeters. Since it's positive, the final image is over here, 60 centimeters to the right of lens 2. Alright, an object 3 centimeters high is 20 centimeters in front of a mirror. The image is upright and 1.5 centimeters high. Alright, so what type of mirror is this? Well, first let's see what we have here. We have the magnification, which is height of the image over height of the object, is 1.5 over 3. So the magnification is 1/2. It also says that it's upright. That means that the magnification is positive 1/2. The only kind of mirror that will make an image that is smaller and upright is a convex mirror. You know, that's like a security mirror where your object is here and this is your mirror surface. Alright? So it's a convex mirror. The magnification is plus 1/2. Where is the image located? Well, I know that M is equal to minus Q over P, and that's equal to plus 1/2. Let's see, so I know what P is. P is 20, so minus Q over 20 is equal to 1/2. So Q is equal to minus 10 centimeters. Q is equal to minus 10 centimeters. So the image is located 10 centimeters behind the mirror. It's a virtual image. What is the focal length of the mirror? Well, F is equal to 1 over Q plus 1 over P. The inverse of that, that's 1 over minus 10 plus 1 over 20. The inverse of that, that is equal to minus 20 centimeters. As you would expect for a convex mirror, it is negative. Red light at 650 nanometers diffracted by a grating with 5,000 lines per centimeter on a screen 5 meters away. What is the distance between the central fringe and the second bright fringe? Well, first we need to find the slit spacing. That's 1 over 5,000. This is in centimeters. If I go ahead and convert that to meters, I get 2 times 10 to the minus 6 meters. This translates into 2 times 10 to the minus 4 centimeters, which is equal to 2 times 10 to the minus 6 meters, or 2 microns. The order number that I'm concerned with is second order, and the wavelength is 650 times 10 to the minus 9 meters. Now, d sine theta is equal to m lambda. I want to solve this for theta, so this is 2 times 10 to the minus 6 sine of theta is equal to 2 times 650 times 10 to the minus 9. And if I solve this for theta, I get 40.5 degrees, which might seem like a big angle, but if you think about the diffraction gratings that I showed you in class, those diffraction spots are spread out pretty far, so 40.5 degrees isn't absurd. Now, I want to know the distance between the central fringe and the second bright fringe, so y is just equal to L tangent of theta, which is 5 tan of 40.5. That's 4.3 meters. Now to sketch the diffraction pattern, I want to show the appropriate number of orders. So let me calculate that first. D sine theta is equal to m lambda. If I let theta equal 90, then I solve for m. That's d over lambda. And this equals 3.1. That means that on either side of the central bright fringe there are 3 orders. So it looks something like this if I just sketch it. There's the central fringe. And that's it. Alright, a Michaelson Interferometer uses a wavelength of light 500 nanometers. As you move the translating mirror in this figure, 300 bright fringes. So you get 300 fringes. Pass a fixed point on the detector. How far did the mirror move? Well, as we said before, the change in your path length difference is going to equal or delta L is going to equal 300 lambda. That is the number of fringes that pass by. You get that many wavelengths divided by 2. So this is equal to 150 times 500 nanometers, which is equal to 7.5 times 10 to the minus 5 meters. Double slit apparatus has a slit separation of 0.2 millimeters. Light of wavelength 630 nanometers is incident on the slit, and the diffraction pattern is 2 meters away. What is the width of the central bright fringe? So d is equal to 0.2 times 10 to the minus 3 meters. M is going to equal 0 in this case. I'll show you why. Lambda is equal to 630 times 10 to the minus 9. And L is equal to 2. Alright, here's my diffraction pattern. I want to know what is this distance. Alright, so I need to know what is the angle to the first dark fringe. Now for a double slit, the dark fringe is d sine theta equals m plus 1/2 lambda, and in this case m will be 0 because it's the first dark fringe, which is associated with the 0th order. So I solve here for theta, which is the inverse sine of lambda over 2d. That's equal to 0.0902 degrees. And then I solve for y, which is this distance. Y is equal to L tan theta, 3.15 times 10 to the minus 3 meters. And so 2y, which is my width, is 6.3 millimeters, or 6.3 times 10 to the minus 3 meters.